Start recording here. All right, so start here at 3:05. Let's see, get my camera rolling. Nice. Very nice. Okay. And then I actually thought there'd be some more questions. I guess I got one, but more from 121. They're in that harder rotation stuff.
This time in the 121 semester was very stressful because we had at this point pretty much just switched to online. So it was like all the teachers were just trying to figure everything out at this point.
Yeah. And it was and you were right at the hard stuff, the rotation stuff. All right. So what was this? 38, number 57. Oh, it's like 57 is one of the ones that wasn't on the PDF here. Oh, good. Another, I can never say this right. Rayleigh Criterion. Rayleigh Criterion. But another one, resolution. And actually, this kind of fits in what we said earlier in a break. We were doing diffraction, and we were talking about the good and the bad. Like sometimes it's good that it spreads out so that, like, you can hear sound around a door, but other times, like when it spreads out, two different sources merge together, and you can no longer detect that there's two. And if you wanted to know there were two or detect the two separately, you can't. They blur together. So there's a good and bad about that. And same thing here. We were doing that with microwaves. Here is the idea of a screen. All these screens we look at, especially in this COVID world, all the screens are actually made out of little tiny dots. We call those pixels. And if you get really close, like, let's see if I get really close to my laptop here. Yeah, I can actually see individual pixels. Okay. But when you step back, the angle changes and they blur together. And so it looks like, a screen's supposed to look like a continuum of colors. Now, they blur together for more reasons than just diffraction. But diffraction is one of the reasons they blur together. And with good optical equipment, the Rayleigh condition or criterion might be the deciding factor. Most of the time with human eyes, the diffraction and the blurring actually is caused from the imperfection of the optics before you get to the condition of diffraction. So this is a good problem, but I would say I like when people do the human eye problem and things blur together, and that's the idea of a screen. In fact, a little bit of history, because that's why the original design of a computer screen, in fact, I'll just read it here. It says the American standard television picture was composed of approximately 485 horizontal lines. And so the early engineers were looking at TV screens, which were under 20 inches. I mean, they weren't, like the TV screens we have today. And they said that, if they were to send a beam of electrons sweeping across, making light, and then a second one, and then a third one, originally there was concern that, it looked like stripes on the TV screen. And like, well, that's not going to look very good. But if you got them close enough, they would blur together. And so it was decided that 485 lines would be a good place to shoot for. Today we call that standard definition television. And in fact, I noticed every time I make like a video solution and I upload it, it starts processing it and it makes the standard definition first. And the high definition actually is a long time coming. It's almost a day later. And I kind of feel bad because I bet a lot of you probably watch it while it's still in standard definition and hasn't been upgraded to the high definition. Although I guess depending on your bandwidth, you probably have an auto set and it probably chooses, well, depending on your bandwidth, you might always get standard definition, but I know you could pick. Anyways, as TVs got bigger, this became a problem. And so what I call high definition 1 came out, and that's 720. But they were shooting for, and the technology just wasn't there to get high definition at 1080. And so that's really high def, although they needed a better word there because high def 1 and high def 2 are different values.
But nowadays the technology is advancing so fast that you can get that 1080 HD in a TV for much cheaper than you could have like 5, 6, 7 years ago.
Oh yeah, I bought this upgrade from 720 to 1080 was just starting to hit the market when I was kind of redoing my living room, and I repainted and took off the old popcorn ceiling and got a new entertainment center. And I go, okay, well, I'm gonna get a TV. And then I realized, wow, if I don't get this one, I'm going to be sorry in a few years. So I go, I'm going to get this one. And there was only 2 manufacturers. I think it was Philips and Sony that were even having it on the market at 1080 at the time. And yeah, I've never paid so much for a TV. I think I paid $2,800 for a TV. I go, okay. And it wasn't even like the TVs of today. It was still, what was that technology? DLL, digital, was it DLL, digital light?
Something like that.
DL.
Yeah, it's kind of crazy. You can get like 4K TVs now for like under $500.
You can get like, you can get small 1080 TVs for like maybe a little over $100.
Yeah,
Crazy. So, well, anyways, so I got carried away again in the growth of technology, but this problem circles around this idea that this was a challenge at its time to try to get 480 lines streamed out here fast enough so that you wouldn't see kind of this striping effect, but they knew they needed to get at least 485 lines to get the screen big enough that the individual pixels would blur together. If you were something like a 10-foot standard, that was kind of their standard. If you were 10 feet away, you couldn't see the individual pixels on a TV. They would blur together. And so, like all of technologies, they're pushing the envelope there, saying, all right, this is what we want to get. We want to get way up to here. This will make the screen somewhat doable. And I'm sure in 1947, this was amazing television. All right, but anyways, that's kind of the background thinking by the engineers. It's like, okay, let's get a goal here, a standard. But it also explains why then once you start getting bigger TVs, this isn't going to cut it anymore. I mean, if you only had 485 lines on some of these, big 70, 80-inch TVs, you would actually see individual lines and individual pixels, and it would look terrible. So you would not be happy. So you got to increase the screen. You got to increase then the resolution. All right. So the American Standard Television is composed of approximately 485 horizontal lines of varying light intensity. Assuming that your ability to absolve the lines is limited, and this is important, only by the Rayleigh Criterion, and like I said, really your eyes blur for other reasons, but and the pupils in your eyes are 5 millimeters in diameter. Calculate then the ratio of the minimum viewing distance to the vertical dimensions of the picture, such that you will not be able to resolve the lines. All right, so understanding kind of the technology is important. So I'll go back to this picture. So let's just say the vertical dimensions of this TV is L. Or should I do Y? Yeah, let me do Y. And then maybe I take a cross-sectional picture in your living room here. So here's the vertical height of the TV. And then you're going to sit or watch from a distance of capital L. Maybe that'll be okay. Yeah, so I'll use the L for this one and the Y for that one. Okay. Now, there would be a line and another line and another line and another line and another line. So the spacing between any two lines would be Y divided by 485. Okay. And the angle then between them, so theta, and I'll use sine theta, but I'm going to use kind of the small angle approximation. And so looking at this as a triangle, the opposite here would be this distance between a line. So this would be 5 divided by 485 divided by the L. And of course, if you kind of simplify this math, you get Y over L equals 485 times sine theta. And this Y over L is what they're looking for. That might be kind of confusing too. Let me come back and read the question. It says calculate the ratio. There it is, ratio of the minimum viewing distance to the vertical dimensions. Oh, I guess I have mine upside down, so let me flip it. But we want this ratio of distance you are from the viewing and the vertical dimensions of the picture. So let me flip my equation. So L over Y is what they're looking for. Would be then 1 over 485 times sine theta. And for it to blur together, this number has to be that or greater. And so for some reason, I kind of remember that they set the standard viewing of a length of 10 feet and 20 inches here for your ratio, thinking that especially the first TVs, which were smaller than 20 inches, people could then actually, once they were at 10 feet or maybe even about 8 feet, they would blur together. And that would be your viewing distances. Oh, by the way, another little fun history fact then, and that's why then when the computer screen came out, they realized right away that the standard 485 that we use for a television was just not going to work for a viewing screen because people don't sit 10 feet away from a computer screen, and so those first computer monitors came out, they're like, okay, we've got to make the screen smaller and or more lines. And once that started, the standard definition just kind of went away, and then people started building whatever they wanted. And I don't even know what my phone is now. And there's probably no point in talking about how many lines, but how close the pixels are, because phones have so many different size screens. Some are big screens, some are small screens. So the number of lines is probably not as important as the resolution, how close the dots are, how many dots per inch or something, or pixels per inch. Anyways, this is what we're looking for. All right. So that's kind of the background. Then we can say, of course, the Rayleigh Criterion. And let me put this on here first, because when we did the last problem before the break, we said this, when you set m equal to 1, was the limiting factor. And although that is not wrong, that is the one-dimensional solution. That is the solution if you go through a slit. If you go through a hole, the light behaves a little different. I mean, it's still going to hit and spread out, but I can't really draw. It kind of spreads out in a two-dimensional way. And instead of getting the first solution to a trig function, it's actually a solution, and this is a function. I don't know if you're familiar with it. It's called a Bessel function. But your book, and so me too, is going to say, well, we're starting to get into, because when you do this, you add an infinite number of pieces in a line. Here we're going to add an infinite number of pieces on the area of a circle. And the solution to that is one of these fancier functions called a Bessel function. Now, Bessel functions are used for many other things. So you'll probably hear that in your math class, a Bessel function, but it's often used for two-dimensional wave stuff. And that's what this would be perfect for. Often, for whatever reasons, considered a kind of, because it's multivariable, I think, beyond the math of this class. You're kind of learning that now. Definitely would be a topic of discussion for your next level of optics. But here's what I am trying to say is, instead of having a lambda over an A, and instead of being the first solution to a trig function, it's actually the first solution to a Bessel function. And the author doesn't explain where the 1.22 comes from, but I'll just state it without proving it. It's 1.22. And the size of the opening would be considered the diameter, since we're talking about a circle instead of a slit. So you put a D here. So this problem would be more appropriately done this way. But I often tell students this semester that if you solved it this way and you replaced, the A with the diameter, and you didn't do the 1.22, I would be happy, give you full credit and say, all right, yeah, you're getting the idea, but technically a one-dimensional slit should be this, and a two-dimensional circle should be this. So small differential in here. So I'm going to go ahead and go with what I think the author probably does and use the 1.22 lambda over d equals the theta. Okay. And I am going to do a small angle approximation. So if I take what I just did and recombined it with what we did earlier, go to the page here. Then I would get something like, oh, maybe I got to get it right here. I'll have 1 over, what is this, 485. And in place of sine theta, I'll just call it theta. And so I'll put 1.22 lambda over d. And that then is this ratio of the viewing distance to the vertical size of the screen.
Are we just plugging in that theta for sine theta because we're assuming it's small?
Yeah. So that's a small angle approximation. And then maybe simplifying this a little bit, that'd put a D on top, a 485, a 1.22, and then a lambda. Now, again, another tricky part about this when it comes to the human eye is the diameter of the human eye changes with light intensity. So, what diameter do you use? Your eye is designed with a retina that opens and closes depending on the intensity outside. So that's one of the reasons people like viewing in a dark room, because it opens up that pupil really big. And then your D's really big, your resolving angle is smaller and you can see details. And there's something to be said. And even more so because when the human eye retina opens up, you get to the part of the lens that's not nearly as perfect and you get more blurring from that. Remember I said that this is a blurring because of the diffraction of light, but your eye actually has a blurring because of the imperfections of the construction of the eye around the rim. So
is that why like often when your eyes adjust to the darkness, you can kind of in a way see better in the dark versus like a really sunny day?
Well, you can see details better.
Okay.
Yeah. But there's other reasons, depending on your definition of seeing better, because it's also, it also can be darker. So, and it also, and I think because of that, also your photorensensors, when you start to get my age, aren't as strong. So, I would say when I was younger, I could see things a little more higher resolution in the dark. But now I think because my photo sensors aren't as strong, I really like bright light on it. It's like, oh yeah, shine a bright light on that. So I really need that light to activate, I think, maybe some of my weaker photo sensors. So. Okay, so keeping that in mind, then I think it's just a matter of plugging it in because I think they gave us the D. Let me look here. Condition for the eyes are so 5 millimeters in diameter. So let me go 5 times 10 to the negative 3. Let me do a divide by 485. Let me do a divide by 1.22. And again, the other thing I was getting at is for the human eye, now that there's so many different wavelengths coming into your eye, and you could look at the extreme, or you could look at maybe kind of an average in the middle. Let's see, what do they say here? Yeah, and they tell us go ahead and pick the middle of the spectrum. Okay. Or they don't say middle of the spectrum. They say 550 nanometers, which is the middle of the spectrum. So I see what they're doing. They're saying, okay, well, we'll pick the middle. But again, you really, you know, if you were kind of engineering this, you probably would want this to meet a certain condition for the worst case. And so the worst case, you might say, well, let's take when this is small during daylight hours, and then this is big looking at the reds, because anyway, it's kind of a judgment call on how you want to define it. But according to this, it's a 15.3. So you want to be at least 15 times further from the screen than the size of a vertical screen for them to blur together. So even these big giant screens at kind of these new drive-ins they have during the pandemic, you know, you can easily be 15. I mean, even though they're giant screens, you can easily be 15 times further from that. So they might get away with a standard definition on their screens. Whereas if you were real close to that screen, you might go, oh, that's kind of blurry. Let's see what the answer key gives us. What did I do with my answer key? Oh, there it is. And this number was this 57? Oh, and then so yeah, so they got 15.4. Oh, good. Nice.
Thank you.
Yes, you're welcome. Hope I didn't talk too much. All right. Little history of technology. We
Hey,
should
I
probably
have a-
do.
Sorry, I have a quick question on number 18, if you can answer that.
Oh, yeah.
On number 18, you get a frequency before you finally solve the problem, and or it's a wavelength, sorry, and it's traveling in air, so it's the speed of light or sound, sorry, and I'm wondering how you got it, because I'm getting a different wavelength.
Oh, well, let me look. You say number 18? Let me look.
Yeah, number 18.
Okay. And actually, let me write this down. Number 18. Looks like we're about 333 right now. Let me scroll up. See what 18 is and decide if you want me to do the whole problem. Oh. Now, wait a minute. I don't see 8. Are we supposed to do 18? Or?
Yeah, it says 18 for chapter 38.
8.
It's in the homework packet too.
Okay. Oh, and my bad. I scrolled too far. I went in the wrong chapter. Okay. Oh, no. Okay, here it is. Oh, I see what I did wrong. I was thinking I was in chapter 38 because I was doing 38, but I was doing it from the textbook. That's right. And then anyway, but I was in 37. All right. I got it now. Yeah, and this is okay. So actually, this is a great one too here. Let me start from scratch. But do you see here where it says a circular radar antenna? And this actually fits two things that I was talking about earlier. The first one is that technically this is not a slit. This is a more advanced two-dimensional one. So without proof and actually solving the Bessel function, instead of writing the Rayleigh criterion as lambda over A, but I would say that I am completely open to accepting that because that's really what's worked out. That's a one-dimensional one. Your author then just throws out without proof, again, mostly because of the math, and then also the solution is a solution to a first-order Bessel function. So it's 1.22 lambda over D. And it makes more sense that you should replace the A with a D. Many students just kind of do that and solve it. And then I'm good with that. But I think I should, since they say circular, use the extra factor of 1.22. So I will. But the other thing that I want to point out here is, again, this is diffraction, and diffraction occurs for all waves. Even though we are spending our time here talking about optics, this doesn't only happen for light waves. And in fact, it's not even just limited to electromagnetic waves. We did a problem before the break where we had this discussion with microwaves, which are still electromagnetic. But this could be X-rays, which again are still electromagnetic. But it could also be sound waves or water waves. And you would have that same spreading out. And so like a speaker with a round opening would make the sound and it would come up and spread. And this would be that spreading, which, by the way, as a side note too, when and if we're ever allowed to go back to movie theaters, if you look at let's say this is the sidewall of the movie theater. So maybe you're in the audience sitting here with your bag of popcorn. And the screen is here. Projector is often up overhead and projecting here. On the sidewall, they will put the speakers. And if you've looked at them closely, you'll see that they are taller than they are wide. And they take advantage of this. The sound engineers know then that the sound coming out of a narrow slit will spread out. And so it's going to spread out over the audience, but it's tall, so it doesn't spread out towards the ceiling or the floor. And then so you want that tall, narrow speaker. So it does that kind of effect. And that would be, again, the same thing, but with sound waves. And anyway, so that kind of reminded me of this when I saw that, hey, here we have radar, which would be way down in the, even lower than the microwaves. This would be in the radio wave ones. Anyways, but now it says here it's on a Coast Guard ship. It has a diameter of 2.1 meters and radiates at a frequency of 15 gigahertz. So as you can see, and I think this was part of your question, that in order to solve this problem, you need to have wavelength. And remembering that wavelength times frequency is velocity. So since these are electromagnetic waves, we can replace velocity with c, which again, we call c the speed of light, but terrible name for it because it makes it sound like only light goes the speed of light. And no, we have discovered that there's other things just like light. All electromagnetic waves are essentially the same. So we really should call this the speed of electromagnetic waves. All right, so I'm going to go ahead and find this wavelength, even though I still got to justify that I need it, but you can see it in that equation. And it's 15 gigahertz. 15 gigahertz. I would put this in microwaves. Now, a circular radar antenna. Oh, and I don't know why I called them radio waves. These are microwaves. But I guess because the acronym for radar is radio wave detecting and ranging. Anyways, the 15 gigahertz. So the wavelength on these, 3 times 10 to the 8th divided by 15 times 10 to the 9, so 0.02 meters or 2 centimeters. So these are, only that big. That's under an inch. 2.4 is an inch. So these are pretty small. These are definitely in the microwave region. And they will spread. But something as big as 2 meters, there's not going to be much of a spread to them. Now, let me go back to the question now that I have the spread. It says the radiation at a frequency of 15 gigahertz. Oh, 2 small boats are then located 9 kilometers away from the ship. How close together could the boats be and still be detected as 2 objects? Now, I don't know if you need to know this, but the transmitting antenna and the receiving antenna, not always, but are often the same thing. So what I'm going to do is think of it this way, that the receiving antenna is this round disc that is going to come in and decide if I can see the 2 objects separated. And so I'll have a pattern from source number 1 and a pattern from source number 2. Okay. And I'll view this as the antenna when it's receiving, because really a moment earlier it sent out a pulse. The radar hit the 2 objects and they're reflecting the energy back. And so that's why I'll think of the 2 ships out there as source 1 and source 2, that they're actually emitting some radar waves. And they're not really emitting it themselves. They're reflecting from what the Coast Guard radar sent out. So it sends it out, boop, shuts down, and then now becomes a listening antenna. So it's a source antenna, sends it out, boop, little pulse, stops, bing, and then picks it. Okay. Or they can have a separate one. Okay. But I think when they say a circular radar antenna, we have to interpret that to mean that the receiving one is that size, because that's where the blurring is going to come into effect. Okay. All right. So coming back to our Rayleigh criterion, for this particular wavelength of radar and this particular diameter, you would be able to see things that are separated. 1.22, here's the wavelength. What was the diameter of this thing? 2.10 meters. So this is the smallest angle they would be able to resolve. So if the 2 ships are together, close enough together, you're not going to be able to tell there's 2 ships. You're going to think you just have 1 contact. And in fact, I understand from talking to some Coast Guard people that that is common, especially on off our coast, because this is where they have the drug runners coming up and exchanging drugs, and the ships will be close together, and the Coast Guard will pick them up and then pursue it. They think they have a single contact. Then they get within a certain distance and they realize, oh no, this is 2 contacts. We got 2 vessels here. We can now close enough to resolve it. So 1.22 times 0.02 divided by 2.1. And so in radians, anything closer than 0.0116, this radar system won't work to resolve them.
And is that equation for circular aperture, or are you calling it, or yeah, that equation, that's always going to come out in radians, right?
Yeah, yeah, yeah. It's always going to be in radians, and I know that because of the units here. This is a meter and a meter, and when you have no units, that's what's meant by radians. We call it radians, but some people prefer to call them real numbers. So when you get real numbers, those are radians. No units involved. Yeah. Yeah, and that kind of reminds me of the problem before the break where within the same problem, we had to do an angle twice in degrees and once in radians, and the radians was in the middle, so we had to switch back and forth. So recognizing, yeah, when it's in radians is not always easy, but it's important to recognize. So look at the units. Actually kind of brings up some other things too. So a lot of these antennas for the fancier stuff, and this is a Coast Guard, so they would have a whole fancy radar equipment. This wouldn't be like a fishing vessel, but or the Air Force in particular, especially like the Air Force AWACS. That's why they can have different wavelengths. There's advantages of different ones. The small wavelength, you can see more details. The unfortunate thing, though, with the short wavelengths, as you can imagine, the short wavelengths don't diffract as much. So they won't bend over the curvature of the Earth. And so if you had a plane here, so here's an AWACS, and here's a bogey plane here trying to sneak up on you. If AWACS sends out this short wavelength so they can see high resolution, this bogey's hiding over the horizon and you don't pick it out. You switch over to long wavelengths and it refracts around the surface of the Earth, reflects off the bogey, and you pick it up. And so they'll switch back and forth saying, hey, I got a contact out here beyond horizon. Sadly, to get a contact beyond horizon, I can't get details. I can't tell you what the shape of the plane. I don't know if it's a cargo plane. I don't know if it's an enemy plane. I know it's direction it's approaching because I can get that from the Doppler shift. But, and of course, oftentimes if it's low to the ground, high rate of speed, that's not a good sign. So, but at least you know before it gets over the horizon where it is. And so, and in case of AWACS, that thing's so powerful, you're hundreds of miles away. There's no threat. Its missile range is too far. So hopefully that's when you have your F-15 over here going, all right, I'll give you this information. Just beyond the hill, there's two bogeys. So, yeah, but that's kind of these different wavelengths and the advantages and, like I said, disadvantages of them diffracting out and spreading around. All right, so anyways, back to this particular problem. If, again, these two ships are closer than that angle, we can't resolve it. But I think we were talking about distance. Yeah, how close could they be? So now let's do this. Let's say this is the radar dish, and the two ships are close together. And we know then, let's just put them right at the limit that this angle in radians has to be 0.0116. And if we just kind of do a small angle approximation and call this an arc length S, and this is the angle in radians, and then this is the distance out, R of an arc of a circle, we know the arc length S, and that'll be roughly the distance between the two ships, would be R theta. And so two small boats are located 9 kilometers. Now I'll change that to meters. So that's 9,000 meters at an angle of 0.0116 radians, no units. And that's going to give me the arc that I would just be able to tell that there's two vehicles out there, or 2 vessels. So this would be 9,000 times, well, I guess the answer before. And so we're looking at about 105 meters. So if 2 vessels or 2 rocks are closer than 105 meters, this particular radar system is just going to say it's one big blob out there. So bigger than that, you'd be able to detect it.
Thank you very much. I appreciate that.
Sure. And then let's see, check my answer. Oh, good. They got 105 also.
Yeah.
Could you show the first page really fast?
I'm sorry, what?
Could you show the first page of the 18 problem that you were doing a little bit earlier? Yeah, that
Yeah,
one.
right here.
Awesome.
Yeah. Oh, and by the way, I had mentioned to you guys that anything that had the Brewster's angle, especially if you're struggling for time, it's good to see, but I would put that in an advanced topic. So I was saying don't do them. And then somebody pointed out that I actually did drop that from the syllabus list because I noticed as I'm looking here at number 30, number 30 is a little bit like that too. It's not a Brewster's one. This is a crystal X-ray diffraction, and it's kind of like the double slit one. But it is a little different, and I'm going to put it in the same category. At number 30, is it? I don't know. Is it on the syllabus there?
So number 30 is on the syllabus. So should we do that after the test?
I'm going to leave that for a judgment call because after the test, so definitely after the test. But even then, I kind of wonder because after the test, we're going to get into modern physics, and you probably going to need to spend a lot of time on that. And
so would it be okay if we just plain out didn't turn in question 30?
Yeah. Oh, yeah.
Okay.
Yeah. That's a better way of saying it. Just if you're, again, that's the Brewster's angle, this X-ray crystal diffraction, polarization by scattering. These things that are right at the end of chapter 38, we just ran out of time, and they're great to do, but they're right at that transition between what we're trying to do, kind of an introduction to optics, and what would be the start of your next level of optics if that's where you go. And I have to emphasize if, because not many people take optics beyond this, because there's no real upper division requirement of optics unless you go into optical or photonics engineering. And many of you probably are doing other things like electrical engineering or mechanical engineering. So it would be okay to pass those, It's like anything, more knowledge is better, but there's a certain limit to how much you really need to know outside of your area before you get overwhelmed.
And plus, once you're actually working in industry, you're going to be working with a team of different types of things.
Yeah. So right. So if if your specialty is not optics, then yeah, you're expecting the member on your team who is the optical specialist to understand this. Oh, by the way, that kind of reminds me. I don't know if it really matters at this point, but another kind of fun one on this whole blurring together. I was doing this radar one and talking about the Coast Guard and the Air Force, but the Army does this really cool thing on their Humvees. The back of a Humvee. So, say this is kind of the back end of a Humvee. Since a lot of times they have to race to a scene in the dark in a line of Humvees, and they want to stay dark, but they don't want to crash into each other. They've got a little rectangular pattern with 4 very dim inset lights. So they only shine straight back. They're not very bright. And here's the idea that the driver behind you, if they get close enough and can see the separation of these 2 sets, they are too close. And you need to back up because there's going to be an accident, and nothing worse than heading to a battle. You get in an accident, not only give away your position, now you're disabled and the enemy attacks you. So you don't want to crash on the way to the battle. So the driver then if the driver just following the Humvee in front sees 4 lights, they know they're too close and they back up. And that will blur these 2 together and it'll look like 2 lights. If they get too far, it blurs and looks like 1 light. Now they know they're too far away. And so that's their goal, is to get 2 lights and leave it there, and just wherever that Humvee goes, you go. Don't look up, don't look down, don't look around, go fast. 2 lights. 4, slow down. 1, speed up, follow that light. Till we get to the battlefield. Yeah. So, pretty ingenious.
Yeah, pretty easy to make sure you follow too. Not that hard.
Right. Pretty easy instructions. Look for 2 lights. Follow those 2 lights. Slow down when there's 4. Speed up when there's 1.
If nobody has any questions, if you wouldn't mind going over 50, that'd be awesome.
Okay.
I was trying to, part C particularly was pretty confusing, the what if part of that question, but if we have time to go through it all, that'd be helpful as well.
All right, let's see, number 50 here. All right, so I'll put number 50. I'll put a time at 3:59. Oh, the very long array. I have dreams of making it to southeast New Mexico and seeing this someday. But not today. All right. But that whole area, the White Sands, the testing of the atomic bomb, the very large array.
Flights are very cheap right now. No one wants to travel.
And if you're vaccinated too, you don't need to quarantine or whatever.
I know.
Yeah.
I know. I keep thinking this is the time to travel. Maybe I should take a little trip. So if I'm zooming next Friday from New Mexico, you know what happened.
Some postcards.
All right, here. So, all right. So number 50. So the very large array. Well, and then also besides the White Sands test range and all that good technology stuff up there, there's also kind of the play on it. There's, you know, the Roswell, New Mexico, and all the aliens, and
Is the crater
and-
in New Mexico or Arizona?
which one?
There's like also like a meteor crater. Is it in New Mexico or Arizona?
Oh, that's Arizona, and that's
okay.
Northeast. I've been there. That's fascinating.
Yeah, I went as a kid. I went through the petrified forest in New Mexico, I guess, and then the crater in Arizona, but I always get them flipped.
Okay, yeah, I think the petrified forest is still in New Mexico. They're very close to that border. It's right there, but that's more off the 40, whereas this is like Carlsbad Caverns is the other one I want to see down there, but that's way down south. That's off the 10 freeway. I've been through Mexico a couple times, but it's always been up along Highway 40. Never seemed to make it to the south. Just yeah. Okay, so here's why this is really cool. It's a set of 27 radio telescopes. Let's see. The antennas can be moved apart on railroad cars, so they put them on cars, and they kind of a Y-shaped device. Well, I guess I made my Y upside down. So a Y-shaped device. But you have 9 on each arm. I'll only draw 3 on each arm. Anyways, and you can move them out, and they essentially change the size of your antenna. And so it's kind of a way of making a giant dish antenna without actually filling up all the space that would be needed for a dish that big. So you get the resolution power of a big dish. You don't get the collecting power of a big dish, but usually that's fine. It's the resolution that they want. And so that's why this is built here, because radio waves have a long wavelength, and to get a high resolution, you have to have a big dish. And so this just increases the resolution without having to build a dish that big. Now, if you built a dish that big, wow, not only would you get the resolving power, but you would get the collecting power. And that would be amazing. But I can't imagine making a dish that's a couple miles long, or even how far is this thing going to be? Yeah, look at that diameter of 36 kilometers.
Yeah, that would cost so much money.
So the antenna can be moved apart on a railroad tracks, and their combined signal gives them a resolution power of a synthetic aperture. So they're looking at a diameter here of 36.0 kilometers. Okay. If the angular, if the detectors are tuned to a frequency of 1.4 gigahertz, what is the angular resolution? All right, so this is, as we've been doing for the last couple of problems, a Rayleigh Criterion one. It's a circular dish, kind of. It's a synthetic circular disk. So, but I'm going to use the 1.22. I'm not going to treat it as a slit. I'll treat it as a 1.22. And I'll also then need, maybe I'll do it here to calculate that wavelength, because usually in the radio waves here, it's kind of tradition to talk about the frequency, not their wavelength. Whereas when you get up into the optical region, it's kind of tradition to talk about their wavelength. So that's kind of an interesting transition. So you can see all the problems we did with microwaves and radars. They're always talking about the frequency. So you need the wavelength. But when we did the optical ones, the visible ones, they always talked about the wavelength, because that's just kind of the pattern that's developed with history. Okay, so I'm going to take the speed of electromagnetic waves and divide it by, I think I saw 1.4 gigahertz. So, oh, this is the 21 centimeter line. Oh, 21.4. Okay. A little astronomy background. One of the best ways to study the universe out there is what's called the 21 centimeter line because their wavelength is 21.4 centimeters. But hydrogen, which is most of our universe out there, has one electron. And if it gets energized, I'll put arrows up. Yeah, maybe it's going to get me too much into atomic physics or chemistry here. But if the spins are in the same direction, they aren't so happy. And they would rather, the electron would rather flip and lose a little energy. And the movement of that electron gives off radio waves of this wavelength.
Okay. Is that
Yeah.
the same for like hydrogen and like dihydrogen or like H2? Like same thing?
No, not
Okay.
even dihydrogen.
Okay.
So out there in the cosmos, there's a lot of single hydrogen. It wouldn't mind hooking up, but there's so few of them they just don't come in contact.
Oh, okay. Interesting.
Um,
But they give off a wavelength of 21 centimeters.
right.
Okay.
And so that's what astronomers use to say, hey, over here we have a large cloud of hydrogen gas. Someday it will condense and warm up and give off light, but right now it's not giving off light.
Mhm.
So how do you detect it if it doesn't give off light? You have to detect it in something other than the visible range. And hydrogen loves to do this. And so that's why they build these arrays to pick up this particular frequency, because now they can see big clouds of hydrogen gas, which with an optical telescope you would see nothing. It's not warm enough to give off any light. Okay. And anyway, so this is a very famous number, the 21 centimeter line here. All right, so I see why they got it tuned to here. All right, so knowing the wavelength, I can then come over to here and say, all right, this is a pretty long wavelength, especially when you compare it to visible light, which is why if you want to be able to resolve something, you need a huge diameter. So I'll put them in meters. So the 21 centimeter line would be 0.21 meters, and the 36 kilometers would be 36,000 meters. And so that means this very large array, VLA, can detect an angular resolution of, so there's the wavelength, times 1.22 divided by 36,000. And so 7.26 times 10 to the negative 6 is the angular resolution, which sounds pretty small. However, you can imagine at that small angle, well, here's Earth, you can resolve anything that is further apart than about 7 millionths of a radian. which again sounds pretty small till you realize you're looking at things really far away. So if we kind of attack this problem like we did the last one, where we can say, okay, here's two objects we want to resolve, s, how far apart, that would be this r theta, where r is how far they are.
So it's probably helpful that we rotate too, so we can actually get everything around it just by panning over, right?
Oh yeah, and actually that's helped. Yeah, that exactly. That's now. Yeah, radio astronomy is kind of interesting. The very first one, well, I don't know if this is the first one. One of the big ones that were successful was that one in Puerto Rico. I don't know if you saw recently, but they decommissioned it a couple of years back, and it finally just collapsed on itself. They were hoping to kind of take the detector down before it rusted out and collapsed on itself. But one of the mini hurricanes that hit there a little sooner than expected. I mean, did more damage, and so they had it's like a security camera on it, and they saw the whole thing collapse, and it went all over the internet. So it was probably what you saw. Anyways, it wasn't functioning. I mean, they weren't taking care of it. There was nothing to it. They'd already decommissioned it. But a lot of these ones they just built in a crater, and that's why Puerto Rico was good. It was closer to the equator. It was built in a volcanic crater, and so as you said, the Earth rotates, so you don't even make it movable. You just take advantage of the Earth going around spinning, and you can sweep out kind of a section of the sky. You can't really, sadly, tilt it up or down, but these can be. These, if you look at the picture, they can be tilted up or down, and then they can use the spinning of the Earth to sweep out. So they can cover most of the northern half of the. It's something like a third of the universe here in the upper half. Of course, I shouldn't say a third of the universe because they're only so sensitive, so they can only look so far away. But the part that they sweep out like a third. All right, but back to part B on this, because I think that answered A. If the detectors are turned to a frequency of 1.4 gigahertz, what is their angular resolution? So this is their angular resolution. Okay, then B, clouds of hydrogen, there it is, radiate at this frequency. What must be the separation distance of two clouds at the center of our galaxy, which is 26,000 light years away, if it's to be resolved? So this is what I started to do for B, saying, okay, how far apart are these two objects we want to detect, these two clouds of hydrogen gas? And we're talking about 26,000 light years for the distance. These clouds that they're studying are at the center of our Milky Way galaxy. And this angle of resolution, 7.26 times 10 to the minus 6. And so this would be 26,000, 7.26 times 10 to the negative 6. And so less than a light year. But it's still a huge distance. Let's see, a light year, let's put that in meters. A light year would be, let's see, the speed of light is 3 times 10 to the 8th. Okay. So that's 1 second. If I multiply by 60, that's the distance in 1 minute. Another 60, that's 1 hour. 24, that's 1 day. 365, I don't know, do I do a quarter? And get that there is 9.4, I'll call it a 7, times 10 to the 15th meters in 1 light year. So if I take that in meters and multiply by the fraction of a light year, we're talking about a 1.78 times 10 to the 15 meters. So what sounded good at the beginning with a small angular resolution resulted in us unable to see anything closer than, let's see, 15 would be a quadrillion. So anything closer than a quadrillion meters is, we can't tell that it's 2 objects. So, bummer. But at least we can tell there's an object there, I guess. So, all right. So if they were closer than that, it would look like just one big cloud instead of 2 separate clouds. Looks like there's a C here, but I'm gonna kind of jump over to solutions here. Okay, what am I in agreement so far? Let's see, 7.26 micro radians. Yeah. They changed it to. Oh, that's interesting. They even changed it. Well, first to degrees, but that was so small. They did it to minutes. That was so small. They went to seconds. So 1.5 arc seconds. I won't bother with that. But then the distance, yeah, they got the same number. They left it in light years. Okay. But I went over to meters. And then let's see, let's go back here to the question C. So C says, what if, as the telescope looks up, a circulating hawk looks down? Okay. Find the angular resolution of the hawk's eye, assuming that the hawk is most sensitive to green light, having a wavelength of 500 nanometers and has a pupil of diameter 12 millimeters. Well, this is a lot like the one we did with the TV. Of course, the TV, we're talking about a human's eye instead of a hawk's eye. But it's the same basic physics that the angular resolution would be 1.22 times the wavelength divided by the diameter. Now, that's, again, the limiting resolution to the physics, what's called the Rayleigh limitations. A hawk's eye may or may not be limited by something before that. The human eye usually is, but hawk's eyes are better than human. So I don't know the answer to that one. But I know it can't be any better than this. This is the physics of the way it is. So 1.22, the wavelength is 500 times 10 to the minus 9 meters. The diameter of the hawk's eye is 12 millimeters. And so 1.22 times 500 times 10 to the negative 9 divided by 12 times 10 to the negative 3. And I probably am going to guess that they put this into the problem so that they can show you that the telescope array is actually about 10 times better than a hawk's eye in terms of resolution, seeing details. Of course, the problem is we're asking this telescope array to see something so incredibly far apart that it's hard to see the things that are, they just sound enormously far apart. They are enormously far apart, but that's because they're enormously far away. But I would describe this VLA as having 10 times the resolutional power as a hawk. And then, of course, but the hawk doesn't really need it because look at here, it says a mouse. So a mouse is on the ground only 30 meters away. By what distance, what the mouse whiskers can separate so you can see them. So kind of doing the same thing that we've done on the last few problems, the arc length would be r times theta. So in this case, the hawk is only 30 meters away, you know, up in the air, maybe about 100 feet, looking down for a meal, and can see things with a resolution of 5.08 times 10 to the minus 5 radians. So taking that resolution and multiply by a distance of 30 meters, 0.0015 meters, which I'll write as 1.5 millimeters. So the hawk could see details that are, you know, 1.5 millimeters apart. That's pretty dang close, especially at a distance of 30 meters. Again, assuming that the hawk's eye is not limited by other factors like the human eye is. I don't know. But in terms of the dimensions of the hawk's eye, it potentially could be this good. Which is pretty, I think, pretty dang good. I mean, you're 100 feet up there and you can see details that are under 2 millimeters apart, just over a millimeter.
Wonder what it'd be like to see like that.
Yeah. Yeah, I don't know. I wish I could just see like when I was 20. So I'd be happy with that.
That's fair, Mike.
But yeah, that's cool. And I'll check the answer here. I was on this one, 50. What is it? C says, it is not true for humans, but we assume that the hawk's visual acuity is limited only by the Rayleigh criterion. Again, they're not saying for sure they know that. So, but all right. They did it and they got 50 microradians. Oh yeah, that's the same thing, which would make a distance of 1.5 millimeters. Yeah, good. Got the same answer. Yay.
Awesome. Thanks for going over that one.
Mm-hmm. You bet.
I want to ask more questions, but at the same time, I'm like, I've been doing physics and math pretty much nonstop today. And I'm like,
Yeah, and this is that time in the semester. I mean, just face to face. I can only imagine online it's worse, but where you just get overwhelmed. I think I was telling you guys that spring semester, I think it's a little nicer to have that week in there. That week can be used for a lot of different purposes, either catch up because you're behind or relax because you're burnt out, but you don't get that in the fall.
it seems like, and it's probably because there's just more like 1-day breaks in spring, but spring seems much faster than fall semester.
No, I know it feels fast for me because I'm transferring next fall. So.
Oh yeah, I can see how.
Yeah.
So you kind of have senioritis right now, Hunter?
I can't afford to. I'm in this differential equations and circuits, so I'm just in. I just need to play catch up constantly.
Yeah. If you've got circuits differential in this class here.
I don't sleep really. It's fine. I'll sleep after the semester.
Yeah.
Ever since the semester started, I haven't gotten to bed before like 1 a.m.
Yeah.
Is circuits hard, Hunter?
After 122, no, not really. Also, I've had experience with circuits and like for years, so like it's not that difficult. It's a little time consuming though with some of the programming assignments because I've never used PSpice before, but I like it a lot. Dr. Arnold, like I took him for Engineering 101, and I really like Dr. Arnold. He's super cool. You too, Mike. Professor Young. Yeah.
Okay, that's fine.
Yeah.
I'm not offended.
Cool.
I might end up taking that next semester or next spring, probably before I leave.
Professor Young, do you have just a master's or a PhD? And then I forget, what is it in?
All of mine are in physics. Yeah. So
Okay.
I did a bachelor's in physics, and then a master's in physics, and then a PhD in physics.
Oh, awesome.
I flirted around with somewhat of the other things like math and engineering, but never really completed them. And I don't regret it. I just found it all fascinating. So yeah, college was an interesting story. I started, and I knew I liked the science and the math. So I came in saying I was a physics / chemistry / math major. I didn't really know. And my first year, of course, was physics and chem, and I kept going. But during the second year, when I got into organic chemistry stuff,
Ooh.
I kind of said, no, forget the chemistry part of it. That kind of made my decision for me.
I feel
Now,
that.
A lot of people's decisions.
later on, when I learned about PCAM, I don't think it would have never changed my mind because I just liked the physics so much. But I must admit, I didn't really. I saw the future in chemistry as being more organic, and I didn't see the PCAM side of things. And then later on, I did, and I was like, I really would have liked that, but I don't, not enough to have change my mind. But then, because when I started taking quantum mechanics, and my roommate was a chemistry major, and so he started as a biochemistry major, and then limited that down to chemistry major, and when he started taking PCAM, it was just killing him, and I kind of really took the class with him. I said, "Oh no, this is just a bunch of quantum mechanics here. This is great stuff. Watch this." So, and so I really liked that. But the one thing I did do is I never did finish. I kept doing the math, but kind of on a second level. I was always doing the physics. And when I got near the end, I went in to see the counselor, and I, had my little plan kind of made out, going, okay, I want to take this class, this class, this class. And he kind of looked at it and he said, well, he goes, wait a minute, am I reading this right? You're at the end of this year, you are going to have completed everything for a physics degree, but yet you want to continue on for a 5th year to get that math degree. And I was like, yeah. He goes, but you want to go to graduate school. He goes, I got a better idea for you. Why don't you just get your physics degree, get your bachelor's, transfer? He goes, wherever, at that point I hadn't been accepted, so I didn't know where I was going to go. He goes, but wherever you're going to go, then go ahead and finish up your degree in math at that school. And I was like, oh, that's a brilliant idea. He goes, you don't want to waste another year of your life. And, he's like, get on with your life. And he goes, and he goes, it really wouldn't change anything. You would just be starting your first year of graduate school in physics while you finished up your bachelor's in math. And I was like, yeah, that's a great idea. And I had like 3 classes to do, and never did them. I just got so involved with physics when I transferred, and stuck to it. So
when did you know that you wanted to get a PhD? Like, how far along into you starting your education?
I was pretty late. And I should probably share this more with students. I mean, our student population is extremely diverse. Some of you come in with, I'll call mentors or models of people who've gone to college and graduate school and know about it. But see, I didn't have any of that. I did not, I didn't even know about, when I started college, I did not even know there was such thing called graduate school. And the neat thing about college is, I think, is they set this horizon for me. And so I was working towards a bachelor's, and it was really kind of about my junior year. I started to learn, and all these other people were talking about taking this other test called a GRE. It was like they were like, well, it's like the ACT, but you take it for graduate school. Well, what do you mean there's more school? What? And maybe by my junior year, I knew that, but certainly when I started, I didn't. And so I like to give the analogy of a horizon because, I set my sights, my selling on this horizon, which would be the bachelor's. But by the time I was getting there, there was a new horizon further out,
Mhm.
and I was
Yeah.
like, oh, there's more to this. And so it really was between the summer of my junior and senior year, I kind of fought with this do I go on? And I finally, as I investigated and looked on, decided yes. Actually, by the way, a big key point to me was I kept saying no because I didn't have any money to go on. I was in huge student debt at that point, going, okay, I need to just make some money here. But that same counselor gave me really two good advices. One, hey, finish up and go to graduate school. And by the way, so that's when I was talking with him, because I decided, hey, I'm going to go to graduate school now, and what do I need to do? And the other thing he pointed out was that in the sciences, you can go to graduate school and not accumulate any more debt because of what they call lab techs. That might be a little
Like doing research, while doing a research assistant work, basically.
Yeah, right. So there's two things. You can be a teaching assistant or you can be a research assistant. But there's so much going on in the sciences and so much money then that you could either teach or be a teaching assistant. You don't really teach. I think I was talking to you guys earlier today that we would have these big classes and then there would be a discussion from a graduate student. That would be the kind of thing I did on my first year there, is I'd go in and run the discussions. And it's considered about a 20-hour-a-week job. And, you don't make a whole lot of money, but it's enough to pay room and board and your tuition. And so, he told me, he goes, look, you can go to graduate school and not accumulate any more debt. And I was like, what? And so I go, I'm going to apply and see. So I did. I'm so glad I did, because that was a foreign world to me. So I was like, yeah.
Awesome.
Yeah, that's pretty awesome.
Yeah, I'm trying to figure out where the upper bar is for myself and where I want to stop, already looking ahead.
Yeah, I'm right now struggling with where I want to transfer, but once I transfer, I'll probably hit the point, okay, do I want to go out in industry and actually work on engineering, or do I want to get a master's or doctorate in this?
Yeah.
So.
Yeah. Well, then, yeah. So if you do work in industry and you are working in engineering, the master makes a lot of sense. I don't know if the PhD.
That's really good for actually being involved more with research and development and less product development side of things in engineering, right? That's kind of my understanding. It's you're doing at that point to try to develop like fundamental components and stuff.
Uh-huh. Uh-huh.
Yeah, I've been looking at material science is what I'm really, really interested in. And so I've been kind of looking at that. It's like you can go the master's route, in which case you'd be like learning skills to go ahead and work in labs, like clean rooms and stuff like that. When you get a PhD, you go ahead and you start like brainstorming and working on stuff like quantum computing technology and like all that.
Yeah.
So, but,
Yeah, that's a good way of doing it. Yeah.
Mhm. Yeah.
Yeah. Yeah, and well, yeah, that would be fascinating for me. And that's not for everybody, but material science, quantum computing, PhD. Oh yeah, that would be.
It just tickles the brain, right?
Yeah, yeah, yeah.
Yeah. Awesome. Cool. Well, thanks so much. I appreciated the insight. Always good chatting with you.
Yes.
I'm